Hello Internet, today I will be demonstrating the physics Rube Goldberg machine that I created in Algodoo, which illustrates Newton's three laws of motion, the conservation of momentum, as well as conservation of energy. So let's start, shall we? The potential energy of the steel ball is converted into kinetic energy as it falls down here. And you can see the math I did over here showing that the potential energy of the ball at the very start is 346 kilojoules. Over here, the steel ball is again going down, and right now you can see that a large portion of the potential energy of the steel ball has been converted to kinetic energy. That amount of kinetic energy is shown right here by this math, showing that at this point the steel ball has 81.6 kilojoules of kinetic energy. Moving on, you can see right here two instances of momentum conservation and Newton's third law of motion. The first instance is when the steel ball impacts the rubber ball. This shows that since the rubber ball gains horizontal velocity, the momentum of the steel ball is conserved when it impacts the rubber ball. Newton's third law is shown as the steel ball impacts and then bounces away from the rubber ball, and when the rubber ball hits and bounces away from the bucket of water, in the opposite direction as illustrated by the law. F12 equals negative F21. Now, this water is going to start going down these chutes, so I'm going to zoom out a little bit and allow you to look at the math again. Because U equal, and then over here we have the potential energy, and here's the calculation of kinetic energy. So we found that the potential energy at the very start of the Rube Goldberg for the steel ball is 346 kilojoules, as shown by the law of potential energy equals mass times force of gravity times height. And right here, you'll see that I calculated the kinetic energy of the steel ball immediately before it impacts the rubber ball using the momentum conservation, or the energy conservation equation. A change in energy equals change in potential energy plus change in kinetic energy. So now you can see the water is most of the way down these tubes going to the bottom of the world, and the turns there are just to make sure that the water doesn't separate, so it kind of all lands at once, or for the most part. So here the water impacting this contraption causes it to rotate, and the water will then get poured down onto it right here, which is going to force this lever upwards and allow the cart to escape. And so the cart begins to move because it has a thruster right here. And the acceleration of the cart is demonstrated by Newton's second law, that force equals mass times acceleration. When we get there, you can see the mathematics, the calculations I did to arrive at the acceleration of the cart. And so here we go, right here. Force equals mass times acceleration. Let's pause it. The thruster provides a constant 120 newtons of force, and the total mass of the cart and the wheels, the whole thing put together, is equal to 141.176 kilograms. So acceleration is equal to the force divided by the mass. And so, as you can see, right here, we have the acceleration of the cart. 0.85 meters per second squared. So the cart's moving along and picking up speed because it's going to need to climb a little bit once it gets closer to the end of its journey. Zoom out so you can see that. And so we're coming close now. You can see the ramp on the right side of the screen as the cart is accelerating more. So we're about to see the illustration of Newton's first law of motion in about 10-15 seconds. So the cart's climbing, it's climbing some more, and here it's going to go off of this ramp and land on this little springy platform and collide with the wood block, illustrating inertia. because, which is Newton's first law, because the momentum or the motion of the cart would continue forward except it was acted on by an outside force. In this case, the block in combination with the springy platform. And so that's the end of the Rube Goldberg machine. And here is the objective: to light up the wonderful sign saying that physics is indeed quite fun. Thank you and have a good day.